Thursday, February 20th. This is CS 746, Perspectives in Data Science. Today we're going to do continue our linear regression lecture with linear regression part 2. So again, we started with the basics of linear regression yesterday. We're going to finish up, do some more detailed stuff about it. I do have the chat up on my screen here, so if anybody has any questions, please go ahead and type them into the chat. And I see some people had some comments earlier while I was trying to get things set up. Yes, the slides were not downloaded to the computer, so hopefully everything's cool. I'll go ahead and make sure that people that are online that can't hear me can read the message. Okay, so linear regression, the main way we do it is OLS, or ordinary least squares regression. There are different kinds of regressions you can make. You can do a logistic regression, other things like that. But the main we're going to do, good morning, is OLS, where we minimize the sum of the squared vertical distances between the observed responses and the responses we predict by our linear approximation. Basically, we're going to try to draw a line with a standard line formula y equals mx plus b. In this case, the intercept beta 0 is what we call in the original formula that we learned in high school algebra. M is the multiplier for x, and b is the intercept. I should stop using that terminology. Anyhow, beta 0 is the intercept, beta 1 is the slope of the line. We're going to take the sum of the distances from all the observations we have. We're going to square those distances, so we penalize things that are farther away more. They have more effect on the line than things that are close to the line. We're going to try to keep the sum of those squares smaller as we can, and we eventually get a minimization problem. So we begin with the minimization problem, minimize beta 0 and beta 1. For that summation, we go ahead and take the first derivative of beta 0 and beta 1 with respect to each of those. You set those both to 0. We can then use linear equations, or linear equations in linear algebra to figure out what the solutions are. We get beta 0 hat and beta 1 hat. Beta 0 hat is a simple one. It's the average of all the y values minus beta 1 hat times the average of all the x values, right? So basically, this is simply the equation for a line, right? So we're just finding the midpoint of our line segment that we've built, and that's where our intercept is going to be by just reversing that equation. Beta 1 hat is a little more complicated. We take the sum of xi times yi minus y bar over the sum of xi times xi minus x bar, which is basically what we're saying here is this is the sum of the products of x and deviation and y deviations from the mean. So how far each x and y point is. Some squared deviations of x and y, the covariance of x and y over n, divided by the covariance or the variance of x over n by itself. So the sum squared deviations of x from x bar. So we take and calculate those summations up, and we get ourselves a beta 1 hat estimator. Now, in these, once we've got this formula, we're going to start trying to decide what variables to put in our model. We have an example we started using on the SAT scores, where we had from 1982, we went to all 50 of the United States, and they measured, what scores were, what the percentage of students were in public schools that took the SAT score, so on and so forth. And they had a bunch of different features on there. So the question is, what is the best model? Some of these features are useful, some of them aren't. So what we're going to do is we're going to consider the 3 types of variables in any one given model. Some of the variables are controlling variables. We've already decided we're going to keep them. They're in a model. They're just fixed, okay? We're controlling for bias selection. These are default variables in order to capture more meaningful relationships. Others are variables that we're trying to see if they explain the response in the variables, explanatory variables, and finally, predictive variables. We are trying to use these variables to see if we can best predict the variability. So when we get new data points that we haven't seen before, right, we can guess what the y value would be of those other observations. So for instance, in the SAT scores, we had all these 50 states. Well, what if we brought in Puerto Rico, Guam, District of Columbia, some of these things that are not states, that are part of the United States, that are still in the same system, take the same tests and things like that. Can we predict what kind of results those would get if we got the statistics for those particular locations? Or, of course, the other possibility is just try a different year when different expenditures are being done by the states, right? Confidence interval estimation. Now, for each individual observation, or I'm sorry, for each beta, when we're doing a multiple linear regression, of course, every individual feature has its own slope associated with it, right? So a single linear regression, we're drawing a line. A linear regression with two features, we're drawing a plane. If we're drawing with three features, we're drawing a solid, as it were, a space, right? And so on, we get into higher and higher dimensions. But each of these has an associated linear relationship between that variable. So for each of these individual variables, we can derive a confidence interval for the slope of that line. And this is the important piece of our estimation, is right, how much do we think that particular variable contributes to our model? If we get a beta hat sub j close to 0, right, then that variable is not predicting the dependent variable at all. If we get a beta hat sub j that's, a significantly higher number, then we go ahead and say that, yes, it's got predictive power. And we look at our confidence intervals to see what that is. So here's our confidence interval, a t-distribution using the sum squared errors, right? So we want to ask ourselves, is beta sub j statistically significant? So, well, the first thing we can do on that is to look at the confidence interval that our model reports back to us. And it's a t interval. Reason why? Because we're measuring features, right? So we're testing what this beta sub j sub 0. Beta sub j is equal to 0 is our null hypothesis. Our alternate hypothesis it is not 0. We don't have very many features. We're going to use a small number of things we're testing. So it's going to be a t-test. Again, t-test, we only use that when we know what the variance of their population is, when we have a large sample space. Well, generally, we don't have that when we're counting out features. So to test the statistical significance, given all other predicting variables are held fixed, right? And using the t-test, if it gets too large, the absolute value of that gets too large. In other words, the p-value gets too small. Then we reject the null hypothesis and say that the slope of this particular feature is not 0. It is a useful model. In the output, and again, I need to upload this for you. We'll get that up here soon, someday. But we do have the SAT data set and the IPython notebook. So when we get that uploaded, we'll go ahead and let you download it and mess around with it. But we're running an OLS model in Python right here. We're getting the ordinary least squares. This is a simple model with only one feature, a simple linear regression. Do the takers help predict the number of takers in a state, right? Help predict the SAT scores. And in the simple model here, it looks like, yes, the number of takers is a pretty good predictor, right? Our confidence interval is between -3.2 and -2.2. Our intercept, oddly, is between 1,000 and 1,036. Neither of these have a confidence level that's covering 0, right? If we look at it down here on the t-test statistic, we see 125 for the t-statistic here. Probability of that of basically 0, to the rounding error. You have to get down to a lot more zeros before we can see what 125 t-statistic looks like in a p-value. When we apply the full model, things change. Simpson's paradox we talked about before, right? Simpson's paradox says that when you start considering things in isolation versus considering things together with all the other variables, you can get different results for individual variables. And we definitely see that here. The intercept with the full model, everything included. We're holding intercept and takers, right? We're using those as our controlling variables. We're keeping them. We're asking ourselves whether to add all the rest of the variables. You can see our confidence interval now spans a 0, from -521 to +331. Our takers spans 0 from minus 1.87 to 0.919. Our p-value on the t-statistic is 65% and 49%. So in the full model, the takers and the intercept, we can see that they're not particularly useful when compared to the other variables that we have available to us. What looks good? Well, income, no. 95% p-value. That's definitely not rejecting the H0 on that. 0.01, here's a p-value, here's a confidence interval. You can see that 0 is not in this range. So years of education or years of taking particular subjects makes a difference on SAT scores. Expenditure by the state on public schools makes a difference. The rank of the students in the class, right, makes a difference. And for trivia, if you care, there's a good reason for this. In the United States, there are two main college admission tests back in the 1980s. There was the ACT and the SAT. ACT was taken by students who were going to attend colleges on the West Coast. SAT was taken by students who were planning to attend colleges in the old Ivy League schools on the East Coast, Harvard, Yale, big names like that. So in states like in California, where they would prefer to stay home, they would take the ACT, would not bother taking the SAT. Only people that were in the cream of the crop, the best students, would even consider going across the country to the other side of the United States. And so they would always be the best students in the class. So the higher the rank, the more likely they would take the SAT. Or the more likely they would take the SAT, the higher the rank they would be. So this is actually reversing the relationship there of causality. So cute, whatever. Here's our p-statistics again, link back to that. Our confidence interval, you can see if we do a 95% confidence interval, which is the default for OLS in Python in pandas, we get, minus 521 to 331. We already saw that. Up here, minus 521 to 331, right? These are just these numbers right here, expressed in scientific notation. Go the right way. But of course, if we demand a 99% confidence interval, it's going to be broader. There's going to be a smaller rejection region for the null hypothesis. So we go from minus 660 to 475. Makes sense? Yes. So everything is wider. And so there are some things that we can see in here that look significant. Here, right here, this one here, between 0.5 and 3.9. And here, this one has gone negative. So this confidence interval, when we go to 99% confidence interval, this particular argument, expenditures, no longer looks like it's statistically significant, right? Now, the next step we want to do is to test, is our model good, right? Are we getting anything out of this? Are we just throwing stuff at a dartboard, right? And so if we have a low confidence on all of our variables, then likely we expect our model is not useful. We have a high p-value. If we see some of our arguments look like they're good, some of our features look like they're useful, we still have to ask ourselves, is the overall model itself, right? Are they actually good, or are we just looking at a Simpsons paradox kind of thing here, right? So the goodness of fit test is an F test. H0 is that for every one of our features, the intercept, feature 1, feature 2, up to feature p, that the slope of them all is 0. They're all useless in predicting the y value. And the H alpha, or H A, is that at least one of them. We don't know which one. We're just saying that at least one of them is useful when compared in total. We reject H0 if the F statistic is large, which means at least one of the coefficients is different from 0 at the alpha significance level. The p-value is F of p n minus p minus 1, and those are two different degrees of freedom on the F distribution. If that's bigger than the F statistic we calculate, right, or the probability of seeing a statistic bigger than our value is going to be our p-test. So go on to the next slide. The F distribution, also called the Fisher-Snedeker distribution, which Snedeker is a great name, I think, right, is a very flexible distribution. is, of course, invented by Ronald Fisher, who is the guy that went out and measured, one of the guys who measured all those flowers in the iris data set, right? So famous statistician from the 1930s because, you know, he did both the math and the measuring. If we have degrees of freedom on both of our degrees of freedom are set to 1, we have an exponential curve. If we have high degrees of freedom on both axes, we get something that looks like it's approaching a normal distribution, right? So it's a very flexible distribution. And again, it's you know, covering however many different features we have, however many different observations we have, things like that. So our goodness of fit test is reported in our OLS output. So we can look at that. And we run our OLS output. We look at the F test, the F statistic. If we get a probability on the F statistic that's, you know, 0.29, we say, well, this is useless. We don't have the right information. We don't even have to look any further than that, right? We just look for the overall, right? In this case, the F statistic is 51. The p-value is approximately equal to 0. 4.1 times e to the, you know, times 10 to the minus 18th. So at least one of the variables is explanatory power. Great. Now, the next step is which of our features is the one that's most useful in explaining it. And again, Simpson's paradox, we add and remove things. We can start seeing variance, inflation factor, things like that. We mentioned that previously. So what we want to do is to build the smallest model that explains the dependent variable, right? If we have 1,000 different features, we don't want to throw all 1,000 of those in there. It'll crunch the you know, computer for at least 20 minutes these days. It used to be weeks. That was a joke on, yeah, Moore's law. Anyhow, so we're going to try using ANOVA for multiple regressions. So we're going to take our regression. We're going to look at our residuals and our totals. So the sum squared regression is the sum of how far things are from the regression line. The sum squared total is how far everything is from the average in the middle of the line. If we had a flat line right across the middle, right, the total total sum squares is just a model with no features at all in it, right? So our ANOVA is used to test the hypothesis that one of the sets of coefficients is different from 0 at the alpha significance level. So better explanation here. We consider our full model. All of our features in here, we'll divide them into 2 sets. Controlling factors, we'll call X, and features that we're trying to decide if we want to add them to the model or not. We're going to call those Z or Z. We're going to say beta 1 for X1, beta 2, X2, so on and so forth, up to whatever P features we have that are held as controlling variables. And then these are the ones we're going to add. We're going to ask ourselves, do any of these new features contribute significantly to the model, right? So we can start off with a model with just one feature. Then we add another feature in. We say, does it contribute? Yes or no, right? And so we're going to basically go out there saying H0 is that alpha 1 equals alpha 2 equals alpha q. In other words, this set of the features, right, are not useful versus H alpha or H alternate, which is that at least one of those is not 0. We're going to use a partial F test. We're going to do the sum squared regression over the sum squared errors for the new slopes given the constant or given the controlling variables over the whole thing as a total, right? And again, if our F statistics is large, at least one of our new ones in there. So again, in this case, we're going to start with controlling factors, X1 and X6, total percentage of eligible students who took the exam, and X6, median percentile ranking of test takers. We're going to hold those as our controlling variables. We're going to test whether these other factors add explanatory value as a group or not. So here's what we get. Given X1 and X6, we test the null hypothesis that the coefficients are 0. So here we get our output from the ANOVA test. The first line is with just our controlling variables, It's not being compared to anything. We're just presenting the residual and the sum squared regression. And then the second line is where the usefulness comes in. Now we say, if we add the rest of the features in, model 1, model 0, model 1, model 1 includes everything. Now what do we get for our residual sum squared regression? What is our sum squared, the difference here, right? And we get an F statistic and a p-value for the F statistic. We're lazy. We're just going to go straight to look at the p-value. We're going to see it's a small number, right? Much less than our threshold of 5%. And so we conclude that we reject the null hypothesis. At least one of these other features here, median income, average number of years, percent of test takers, and state expenditure, has an impact on the model. So this is how we can get into, yeah. And again, if we look at our partial F test, we see the F value, 8.622, p-value, approximately 0, yeah. So again, we're going to start moving into future lectures into variable selection. How do we decide which of our features are going to put in the model or not, right? And these are the tests we're going to use to do that. So inference on the coefficients. In this case, we're testing the H0 being that income, public, years, and expenditures is equal to 0. Our F statistic, we came back with sum square regression of those 4 features given the 2 controlling features. We had 50 minus 6 minus 1 is going to be our degrees of freedom on there. So F of 4 and 43 is going to be the F statistic we're going to compare it against. That'll give us a p-value. It's approximately 0. Thus, we reject the null hypothesis. And we say that at least one of those is going to be useful. Okay, great. Now we want to understand how can we estimate our regression line, or how confident are we in our regression line? So our regression lines not only have, a best value that we calculate, they also have confidence intervals and how, possible it is that we're off a little bit on that, right? So our errors on our confidence interval on our regression line or regression plane also have a normal distribution of the residuals, so we can go ahead and look at those. So at some selected value of x, say x star, we'll go ahead and estimate the mean response of y via y given x star is beta 0 plus beta 1 x1 star plus beta 2 x2 star plus so on and so forth. So basically pick a particular observation in there, what would we expect the mean response of y to be at that location, right? These are normally distributed, so y hat is also normally distributed. That means we can draw an inference on the regression line if we know the expected value, which is given to us by our regression line itself, and the variance. Y hat has a normal distribution with our expected value is the regression line. Our variance is calculated by using some nice matrix algebra. We can replace that with the estimator, and we will get a t distribution with n minus p minus 1 degrees of freedom, etc. Going through a lot of math here, which I'm just going to gloss over, but eventually we end up with a nice y hat statistic that is the mean response for one instance of the predicting variables, and is basically telling us, how confident are we that at this particular spot in the data, the confidence interval is this. For all possible instances, we go ahead and have summations in here using the matrices. Now, we can do this for an individual observation in there, or we can go ahead and say, if we had a new observation, and we got this for the percentage of test takers, and this for the state expenditures, and so on and so forth, we could ask ourselves, what value of SAT score would we predict giving that? So we can do, a new observation. We could predict, given, a new set of values, whether we go out and collect those by, looking for the next year, by looking for a territory, maybe for something like that. or just make something up. We can ask ourselves, what kind of prediction would we get? And what would be our confidence levels on that prediction? How wide would our range be, for expected values for the y hat value at that point? So estimated regression line is interpreted as the average estimated mean response for all settings under which predicting variable is equal to x star. If x star is a new observation, it is one setting under which predicting variable is equal to x star. So again, we get down to the basic reason for doing linear regression, and that is to predict future responses. We're trying to draw a regression line. We're going to say, if in the future, if using rainfall to predict crop yields, if we get a really wet year, do we have a good regression line that predicts our crop yields in the future, right? So this is the estimator for the mean response, but it's not the same as the line estimate because it contains two sources of uncertainty. One is due to the parameter estimates, which we've made, and all those bring in a sense of uncertainty, but the other source is the new observation itself. We're not sure what it's going to be. It's an uncertain, whether we've got everything completely accurate in that or not. So our variation of the regression line is with this formula. Our variation of a new measurement is this formula. When we start doing those together, we end up with our new observation has simply the estimated, just sum the two together, right? So the variance of the new observation added to the model. Yay. Now, looking at our multiple linear regression, we need to look at some of the assumptions that we're making about it and verify whether these are accurate or not, right? Are these assumptions correct? And the answer is, in some cases, it's never going to achieve 100% correctness on these assumptions. First of all is the assumption of linearity, that the relationship between x and or y and x sub j is linear for all predicting variables, right? If we're measuring something like something that's seasonal, we'll see a sine curve. We won't see a linear relationship. If we're measuring something that's like, the volume versus area, right? The cube squared law is the area increases by a square, the volume increases by a cube. So that's not a linear relationship, right? We assume that our variances are constant, that at high temperatures, the variance is the same as at low temperatures, right? We assume that independence of the independent random variables, all of our features, E1 through En, we assume they're independent of each other. This is also not necessarily true. Looking at the SAT example, if states spend more on education, then we would just intuitively assume that students would do better. In reality, that may or may not be true, but there's just an assumption that those are actually correlated with each other, right? So those are probably not independent. Normality assumption that the errors, the distances of those y values from the predicted linear regression, we assume those are normally distributed. And again, we have to verify that all these are true. So as we build our model, we're going to stop and take a look at it and look at some graphs and statistics to tell us whether those assumptions are correct or not. So properties of errors. The properties of true errors are that the expected value of the error is 0, and the expected variance is some sigma squared sub I for each of the individual features. Properties of our estimated residuals, epsilon hat, y minus, again, the x matrix, the y matrix minus the x matrix times beta hat. So this is just a shorthand notion, right, for our formula. The estimated value of those errors is going to be 0. The variance is going to be this formula where H is the hat matrix and H sub I is the ith element on that hat matrix diagonal. So while the true errors have constant variance, the estimates do not. So in order to use our estimated residuals, we need to standardize our equation. We're going to divide by 1 minus the square root of 1 minus the H, the ith element on the hat matrix for each observation, right? And so we get that formula, standardized residual values. We can then plot those residuals. We can plot them versus each predictor to see if they look linear. So look at the residuals versus the SAT score. If we see a curve in there, we say, well, that may not be a linear relationship. We can look at it versus the fitted values, see if our variance is constant. We can look and see if our features are independent of each other. We can use a QQ plot or a histogram to test whether these are normally distributed. And we'll show each of these in the next few slides. So we're going to evaluate the normality assumption using the residuals of the response variable, not the response variable itself. We're looking at how far away things are from the regression line, the residuals specifically, right? We're not going to check the predicting variables for normality. However, it is possible that if we see really skewed predicting variables, if we have some predicting variable that's got all the numbers are clustered in one clump, that it might not be normal. So you know, if you haven't collected your data correctly and you have a feature that all the values are the same for that feature or similar to the same, then maybe you've got a feature that you don't need to have in your model. Kick it out, right? So here's our residual analysis. This is a residual plot. Imagine we have our scatter plot of x on the horizontal axis, y on the vertical axis. We've got our diagonal line going up and to the right or down and to the right, right? And our cloud of points. Now we're going to go ahead and take that line and we're going to flatten it out. We're going to take, this is our regression line, renormalize to be flat. We want to look at our residuals, and in this case, we want there to be no correlation. We want this to be just a random looking cloud. If that scatter is not random around that zero line, it could tell us our relationship is not linear. It could tell us that our variances are not constant. It could tell us that our response data are not independent. Here is nonlinear relationship. Here's our zero line. This is where our regression line is. Our residuals around that line start below, go above, go below. This is clearly a nonlinear relationship between x and y. Here is a scatter plot where you can see that things are close to the regression line at low values of x and farther away at high values of x, right? For instance, if we're using like, say, tried this one yesterday, I think it'll work. If we use like height to predict weight of a person, right? And maybe we find out that we're going to use age and height, age to predict weight, and we'll find out that maybe younger people are all clustered around the same weight, and as you get older, some of us eat more, some of us eat less, and the distribution gets wider and wider, and so age is not a good predictor of weight of a person, maybe something like that. So not the best example. I'll come up with a better one later. Anyhow, so this is called skedasticity. Skedasticity is the scatter. Is basically a Greek word. These people were making all this stuff up back in the 1930s. They were all like enamored of ancient Greek and ancient Latin, and so they had to use fancy words for it. So a constant variance, or homoskedasticity, if you draw a couple of lines around the outside, they look horizontal to the residuals. If you have decreasing variance or increasing variance, those lines will look like they're slanted, right? What you're not going to see is this line going up and this line also going up, because that would imply that you didn't get a good OLS plot, and you didn't draw the right beta values for your line, right? So it's going to look like one of these three in terms of the variance, right? So here it could be that S squared, the variance, is not constant. Independence. This is a little harder to see, but if you see clumps in your data, and we've drawn nice little boxes on here to make it easier to see, would have been nice to animate those, I guess, right? But using residual analysis, we check for uncorrelated errors, but not for independence. It's a more complicated matter, If the data are from a randomized trial, then the independence is established. Most data is from observational studies, and so we have to like look for clumps in our data like that and see if we have two features that are related to each other. So the overall comparison of good residuals, assumptions met. Here's our line that we failed to draw in here. That looks like a great plot of residuals. Here's a heteroscedastic plot. Here's a nonlinear plot. Here's one that's got both heteroscedasticity and nonlinearity. We want to check the assumption of normality. The way we're going to do that is what we call a QQ plot. So a normal distribution we think of as a bell curve. If we plot the cumulative normal distribution, we get kind of an S curve, which starts out flat, curves up steeply in the middle, then levels out at the right end, right? And if you want to see whether things are following that, you can try to plot them and see how far away the dots are from that curved line, right? Well, what the QQ plot does is it stretches and compresses the x-axis using this formula so that the standard S curve of a normal distribution cumulative plot turns into a straight line. And then we got some boundaries that we've drawn on here to show how it kind of is more uncertainty at the extremes, right? But this is basically a cumulative normal distribution, squished and compressed. And these are observations on a scatter plot about that. So that's using what we call a QQ plot. Quartile, I think, is what that stands for. R sub I is the rank of E between 1 and n. And F is the cumulative normal distribution. The y-axis, of course, is the errors, the residuals. If you see curvature at the ends, that suggests that there's non-normality. Here's some examples. And you can also be looking at the histogram plot, and this will tell you as well whether you've got normality, but it's harder to see than with a QQ plot. Here we have a histogram where you can see that things are skewed a little bit left of the mean, right? And our QQ plot will show us, it kind of goes up above the plot where we have more observations than we expect. It drops down below it here where we have fewer observations than we expect. Here's a more severe case of the same, right? We have observations. It looks pretty good towards the middle, then drops well down below here when we have a gap in our data. Here we have an outlier at the high end. And you can see our curve is going pretty well. It's a little below, but then it jumps above. This is telling us there's outliers going on in our data, probably. Right? Here's a bimodal curve. It starts out above, goes below, goes back above, goes back below. We can see the two bulges of the modes in the two different modes in our curve, right? So these are all slightly non-normal distributions, and they're easy to pick out in the QQ plot. You need to look at the numbers to verify it, right? But it's also good to just look at the visuals because that's the way our brains work. Another way to check the assumption normality, of course, is simply to look at the histogram of the residuals. And if we see a nice bell curve, we say that that's a good normally distributed. If we see a long tail on one side, we say, well, this is not necessarily normal. If we see a huge gap in the data with outliers, it's definitely, there's something wrong with our normal distribution in that case of our residuals, right? So if our model doesn't fit well, if our QQ plot looks nonlinear, right, it does not necessarily mean the regression is not useful. It could simply mean that you have a relationship that is not exactly linear. So we can do transformations. So for instance, what if instead of using x, we take x and raise it to some power? You know, maybe y is related to, you know, the cube power of x. So if we're measuring, you know, the length of an animal from nose tip to tail, right? And then we measure the weight of that animal, the volume of the animal, right? We're going to see the weight and the volume increase as a cube of the length in general. It's not going to be a linear relationship, but it is going to be a strong relationship, right? Or f of x is the log of x. We start seeing, like, you know, GDPs of nations, and we start trying to plot those, and we'll see that, you know, that there's a logarithmic kind of a formula that explains things like that better than a linear relationship between, like, say, population and GDP. So for normality, assumption does not hold. We go ahead and do some transformation. We're going to use what we call, we take y to some power, I. And these are the common Box-Cox transformations. So if we say I equals 2, we're saying y squared, quadratic. If we say I equals 0.5, we're going to say that y is the square root. We're going to try to see if we get a square root relationship. If we say 0, we're going to say it's a logarithmic relationship, right? And so on. So we're trying these transformations. This is called Box-Cox after the mathematicians that came up with it in the first place. So we have a lambda parameter that tells us, right? And again, L and lambda. Lambda is just the Greek letter for L, or L is the English letter for lambda, as you prefer. So we can use our software to tell us, which value of lambda on our OLS gives us the best regression line. So we're curving our surface using this parameter, right? Outliers. Outliers can mess up your data, but they also can be extremely important in your data. So any data point that is far from the majority of the data, here's a clump of data, here's a point way over here on the right, here's a bunch of data, and here's something that's way above the regression line, right? So data points that are far away in either the X or the Y direction or both are called outliers. If they're far away on the X, they're called leverage points because they have the potential to affect it more strongly than if it's just an outlier in the Y direction. This outlier here can pull the curve up or down. It's not going to change the slope significantly. Okay? This outlier over here, because it's not anywhere near the line, if we include that point, we get the red regression line. If we pull it out and ignore it from our model, it's a completely different slope. So that is an influential point. Its presence definitely changes the model, right? So upshot, sometimes there are good reasons for excluding subsets of your data. Maybe there were errors in the data entry. There were systematic errors in the experiment. You found out, maybe the person who was measuring it was reading the wrong side. There's a famous story that the composer Ludwig van Beethoven was reading the wrong end of his metronome, and so that's why his symphonies, are like impossibly fast. So some of them. Sometimes the outlier belongs in the data, right? So again, we've got an outlier. It's just far away from the other data. If it's far away in the X direction, it has the potential to be influential. If it's far away in the X direction, but also is right on the regression line, that it is not influential. It's just a leverage point that if it had been different, would have made a difference, right? So we think of this as old Archimedes with his lever. Give me a lever long enough, place to stand, I can move the whole world, right? A leverage point has lots of leverage. It has a potential to move our curve significantly. Again, a point. Now, if it actually does change it, and we can test that simply by removing it from the analysis and seeing how much the line moves, right? Then it is an influential observation. So, example, this unusual point. High leverage, large residual, is it influential? In this case right here in the middle, we're going to start here. This has a large residual. It's very far away from my regression line that I'm going to calculate. But it does not have a high leverage. It is not far away in the X direction. It is not influential. If you get far enough up here, it can become influential, right? But in general, we assume that things are not going to be influential. We're not likely to see an influential data point unless it's far away in the X direction, right? So in this case, adding or deleting that would probably just pull up the curve a little bit without changing the slope. In this case, this data point is far away in the X and the Y directions. So it's a high leverage point. It could make a huge difference. But because the line passes right next to where that point is, it doesn't have a high influence, because why? It has a small residual. Over here, of course, is a point that has high leverage, is influential. We don't have a whole lot of data points in this one. So when we add this, the residual compared to the other points, because it pulls the line down, makes the residual for all these points bigger. It's not a particularly huge residual. It is sizable. It is not a small residual, but it's not large either in this case, right? If we had a whole bunch of data points up here like this, and then down here, then we'd see that it had a large residual because it would pull it down, make a difference, but all these points up here would keep the model closer to that curve and give us a higher residual in our outlier. So again, often our regression line will vary greatly depending on what subsets of data we include, right? So we have to decide which ones to put in. We're going to use what we call Cook's distance as a metric. So take our fitted values, y hat sub I. These are our values without observation I included. So we're going to exclude one particular observation, right? And then y hat is the fitted values with everything included, the full model. So if we exclude this particular observation, we get a difference. We transpose that, multiply it back by its original self. We divide that, and we get ourselves a number we call d sub I. If we get a d sub I bigger than 4 over n, where n is the number of observations, or if we get a d of I bigger than 1, any large value, you really should look at it. We can do what we call an outlier plot, and where the Cook's distance is represented in the size of the dot itself. So this is, in fact, using the SAT data set. And when we draw this plot, when we see Cook's distance that's bigger than 10, it's going to A, draw a bigger dot, and B, put a number above it telling us what the Cook's distance is. So you can see we have a significant outlier here, right? And some other distances down here where the distance is pretty far away, but maybe it's not so influential to it, right? Whatever. The influence plot is what we call this. So we'll see that in the code when we get the example uploaded. So examples of a residual analysis. We want to look at, do our assumptions hold? We want to look at graphical displays. If assumptions do not hold, are there transformations we can use, box, Cox arguments, maybe do a time series analysis on there. Does the residual diagnosis improve with our transformations? And then look for outliers. So of course, the pair plot is a great way to look for, testing our linearity and independence. If we see this, we see a couple features that look like they're, connected to each other strongly, right? We also can look at our residuals to see if our residuals look like they're linear. In this case, something funky's going on here. We have a value way up high in the expenditures, way down low on the percentage of public school takers, right? We can look at the Jacques-Barré test or the QQ plot for normality. This will give us a probability using the chi-squared and give us a numerical output to fit with this QQ plot. These things look like they're far away on here in the middle, but the middle of the curve is where it's okay for things to vary a little more. That's where most of our data is going to be. It's if we see things far away from the line at the ends that we start to reject it. So this looks a little funky down here, but we look at our chi-squared two-tailed, we see a 22% on our p-value. So we're not rejecting the null hypothesis. We're assuming that normality of residuals holds. Constant variance holds. Brush-Pagan is another test that will be run in our OLS output. Will tell us whether our data is got constant variance or not. H0 courses that our errors have constant variance. H alpha is there is heteroscedasticity. In this case, it'll draw us a curve on there, and it shows that there is some variance going on. but it's not far enough away for the p-value to be significant, right? So we don't reject the null hypothesis, assume constant variance holds. So we can't just eyeball these things. We have to actually look at the numbers, right? R squared is our coefficient of variation, a determination. So this is a single statistic that tells us how well can our features predict y. We'll use the R squared value, 1 minus the sum squared errors, or this is called the sum squared regression, divided by the sum squared total, and that's R squared. So sum squared errors is all of our little errors. We're going to subtract that from 1. We're going to divide that by the total variance of all of our individual dependent variable observations from the average of the dependent variables, sum squared total. Basically, we're saying this is the proportion of total variability that can be explained by the regression model. We're going to use f-test. F0 statistic is the mean squared regression over the divided by the mean squared error, which is about an F statistic with these degrees of freedom. And again, these are calculated by SSR and SSE. So it's another way to write R squared, SSR over SST. Now, the thing we see on here that's interesting is as we add features, right, our mean square error is going to get bigger. So as we add more predicting variables, what this means is that R squared never decreases, right? So if you just look at R squared as your evaluation for how many features you should put in your model, it'll always tell you add more features. This is why there's a adjusted R squared. Where we subtract this, we penalize based on every new feature we've added. So if we add another feature, this term will go up, right? This term will also increase because the n keeps going up. And so as we add these in there, we generally penalize more terms. So our adjusted R squared, some people will tell you, is a better term to look at than R squared. We'll see both of these statistics on the OLS output. R squared and adjusted R squared. Correlation coefficient, statistic that efficiently summarizes rho, the correlation of x and j, sum of the y observation for each of these distances from the mean over the square roots of the summations. We can use this to evaluate the linear relationship between the response variable and the predicting variables. Use it to evaluate the correlation between the predicting variables for detecting dependence among variables. So this is where we're looking for multicollinearity, variance inflation factor. Quick description of the variance inflation factor here. Again, in order to estimate values, this is the transformation we use. Beta hat is x transposed times the x matrix inverted times x transposed times the y matrix. And we can't invert things if they're linearly dependent. So if we got two columns, two different features that are varying 100% in lockstep, then a matrix algebra is not invertible at all. So this fails. We would get an infinite standard error of beta hat, right? So near collinearity gives us an artificially large beta hat. If one value then changes only slightly, we can change our regression coefficients dramatically. Our overall statistic may be significant, but we look at the individual t statistics for each individual feature, none of them look significant. Right? The prediction is affected since the relationship to the response likely will change in the presence of collinearity. This is, of course, variance inflation factor. The way to calculate that, 1 over 1 minus r squared sub j, where this is for each individual feature, variable j. This is how much of the variation of this variable is explained by the other features in the model. So what would have been the value if there had not been correlation? And a good value for VIF is less than the maximum of 10, or 1 over 1 minus r squared of the model, coefficient of variation of the regression model. So another question we ask ourselves in our analysis, what are the correlation coefficients between each of the quantitative predicting variables? Right? Do we see any potential multicollinearity? So we have to run this as a test against our model to see if it's a good model. So in order to do that, we go look at the variance inflation factors for each of our features. Do we see any potential multicollinearity? If we do see that, right, then we have to find some way to either eliminate one of these multicollinear features or use what we call principal component analysis to reorient the axes of our model and kind of combine these multicollinear features into one single feature significantly farther out in the class. So here's an example. We look at our correlation table. We see that here's a strong negative correlation between features 1 and 6. We look at our variance inflation factors. We see that the variance inflation factor for 2 of these, of course, term 0 is a constant. Here we got 2 of these features down here, feature 1 and feature 6, the 2 that we see in our correlation table as being strongly correlated with each other. These are greater than our threshold. Coefficient of determination is 0.879. Thus, this model explains 87.9% of the variability in the SATs, right? But we do have collinearity in there. Another thing we're going to look at in our output, some of our summaries, normality test. We talked about the Jacques-Barra. You know, are residuals normally distributed? Look at the p-value. If it gets too small, our residuals are not normally distributed. We look at Durbin-Watson. We expect to see this value close to 2. If it's far enough away from 2, we start saying maybe our errors are not independent of each other. Constant variance, we look at the probability of the omnibus. Again, if this is below, say, 5%, we start saying that maybe our variance is not close enough to constant for us to be confident in our model. Finally, oh, we're barely going to finish here. Categorical variables. We have to find somebody to deal with a categorical variable. So the example here is we are an insurance company. We want to charge the proper insurance rates for somebody. We know that older people tend to get more insurance, tend to have more health problems than younger people. So we're going to charge more for old people, right? We expect the people that have a higher body mass index, which this is, you know, is a metric for where someone is active or not. People that tend to be more active have a better health. People that have more children will have more use healthcare more because there's more people to get sick in the family, right? And then people that smoke have a higher likelihood. So we have to find some way of using something for this categorical variable. It's either a yes or a no, right? So what we do is we look at our intercept and we say that is our base cost for a non-smoker, because when the intercept is where everything is 0, right? And so then we look at what their value is of our model with the smoker variable. We basically have a variable we set to 0 or 1, yes or no. And if we see this is significantly different than our intercept, then we say, yes, there is, it contributes to our model. Useful. Okay, good enough for that. That's the end of it. Let's go to, okay, so first of all, people that are online, please go ahead in the chat. Type your name into the chat if you're online. Okay, people are in the room. I'm going to stop sharing. Going to stop the recording. Well, we'll leave the recording running for a little bit longer. I'm going to go ahead and pull up our attendance. And I don't know what this attendance quiz looks like, but we'll go ahead and make it available. Copy, close. So those of you in the room here, go away. Nice. Those of you in the room, that's your code for demonstrating that you've been present in the classroom today. If you go ahead and sign on to the quiz and take that. And again, it is short on time. If you want to just answer a couple questions and skip out the door, that's fine. Okay. I assume everybody else is typing their name in. As you get your name typed in on the online, you can go ahead and sign out because I don't think we have anything more to talk about for class today. All right. So it's important to notice, to mention before we close up that I actually had to steal the lecture from last semester because it wasn't available online when I started the class here. It's on my laptop, but the podium computer was not accessing it. So if we find significant differences, because Hardik was out there going to make some small changes, if they're significant, we'll go ahead and send out a note or talk about it on Tuesday and see what the differences are. Otherwise, I think we're good to go because I don't think there was any significant changes to this lecture from last semester. So yeah, ending the recording now.